Okay, so yeah, for those of you who don't know me, I'm Colle from Brian's Basin. So yeah, we're very pleased today to have Kevin to give the seminar today. Kevin came to us. He got his BS in Michigan in physics. And then he got a master's in space physics as well as a registered certificate in science, technology, and public policy before getting his PhD also from Michigan. So after that, he went to Washington, D.C. to actually work in policy for a year as the AGU AAS Congressional Science Fellow. Before joining the ANCA as an ASP, the Advanced Study Program, postdoctoral fellow, which is a very prestigious fellowship program. And then since last year, January 2015, he's been with us one of the faculty members. So he's going to talk about high resolution climate simulations for projecting changes in extreme weather.
Cool. All right, well, thanks for the introduction. So today I'm going to kind of give a different talk than I normally do. It's going to be kind of an overview of a lot of projects that I've been involved in, but not necessarily the lead on, as well as actually towards the end I'm even going to present some other research from other colleagues that have been diving into this area as well. But first, a lot of these simulations generally require on the order of 5 million computer hours to run, and they create data sets that are on the order of 40 terabytes. So all of this stuff that I'm going to show requires a huge list of people that have been involved at some part, and I've probably left a decent amount of people off the list that have been involved. So none of this work is just my own. It requires the work of generally at least 10 to 15 people to do it. So what I want to do is start with some initial points, some initial actually conclusions, just so if you fall asleep, you'll at least be able to take something away from the talk. So I would argue, and I hope to show you, that we're kind of entering an era where climate models are actually approaching weather scales. And what this means is at high resolution, at high horizontal grid spacing, these climate models are now being able to be run at resolutions that will greatly improve our ability to model multi-scale phenomena, as well as project regional impacts of climate. And together, what I hope to show you at the very end with some results of other colleagues is that these type of simulations and this work can have real applications, and I assume will, have many applications to other disciplines as well as to local community decision makers. But first I want to start with motivation. Why extreme weather? I think that most of us probably have a good idea for what this is. But extreme weather is kind of the way that we experience climate change. And so here's just an example of extreme weather that we are kind of used to, at least in our area. We can have flooding as well as these snowstorms and hurricanes, as we've seen in the past. But other regions of the United States have big impacts due to severe weather and tornadoes, as well as, if you've seen the news at all in the last few years, drought such as the one that's been going on in California. And these impacts are large. And so here's just a schematic of the billion-dollar disasters, weather disasters that occurred last year in the United States alone. So there's 10 of them. And you can see the first thing to notice is that it spans the entire U.S. The impacts are obviously different depending upon where you are. But it's been a pretty common now for the last few years to at least have 10 of these billion-dollar weather disasters. And they can be arranged from a lot of different things. So here you have kind of our big snowstorm and cold snap we had last February. Here you can kind of see impacts of the western drought, which has led, has Alaskan wildfires. I'm not sure why they put that down here, but I guess it's also western. You have tornado outbreaks. You have the flooding, severe flooding, coastal flooding that's occurred. And so the impacts of these extreme weather events are quite far-reaching as well as diverse. And so just an example of this, which a lot of my research has focused on personally, has been changes in tropical cyclones. And so tropical cyclones are actually interesting because they are an important component, actually, of the Earth system. And so they impact large areas, particularly in the tropics, as we've seen ourselves here with Hurricane Sandy. They can have huge impacts, well into the billions. They're actually the costliest of geophysical phenomena in terms of damage and the most lethal through the last 100 years. And they're actually an important component of the Earth system because they actually do transport large amounts of energy and moisture from the tropics to the poles. So not only are they, they're important from the impacts on society, but they actually have huge impacts on the actual atmospheric circulation. And so just to put this in a little bit more context, this came from the third National Climate Assessment. I'm just going to read this here. It says that changes in extreme weather events are the primary way that most people experience climate change. Human-induced climate change has already increased the number and strength of some of the extreme events. Particularly, this is related to extreme rainfall events. Over the last 50 years, much of the United States has seen an increase in prolonged periods of excessively high temperatures, heavy downpours, and in some regions, severe droughts. So the argument here is not only are we trying to understand how extreme weather is going to change in the coming 100 years, but also to understand the changes that we have seen somewhat in some of the records that have occurred over the last 50 years. And so another way just to look at this, I guess, from a big picture view, this is just a time series of the number of billion-dollar events in the United States, billion-dollar disasters due to weather. And so you can see, again, the colors represent all the different flavors of what they can be, anywhere from winter storms through flooding to drought to severe weather and tropical cyclones. And these have been normalized due to inflation. So these would be, so if you were to not look at inflation, obviously some of these events wouldn't have been $1 billion, but they've been adjusted for that. And you can see that there has been a clear, at least somewhat trend in the number of these billion-dollar events. And the lines here actually represent the actual cost of those events. And so you can see here in 2005, there's a huge spike due to Hurricane Katrina, which had huge impacts. And so a lot of these, you can't just say that this is climate. I mean, it's possible that it's not climate. Obviously, there's a lot of possibilities for this, such as decadal oscillations in these type of the flavor of weather events, as well as, obviously, there's been changes in the demographics of where people live and how vulnerable cities are or heavily populated regions to certain types of events. So there's a lot going into this, but we do know that their impacts are changing. We're getting more of them. And so the idea is that numerical modeling of extreme weather in kind of these climate models, these general circulation models, can be useful. But to date, there's been several gigantic challenges, mostly model resolution. So the idea that typically, and I'll go into this in a second, a lot of these events aren't resolved at the scales that we've been running climate models for the last decade or so. Within climate models, we have to parameterize a lot of subgrid scale processes since they're not resolved, such as clouds and convection. And so for most extreme weather events of the wet variety, convection is crucial. So if you're parameterizing it, you're obviously going to probably have some biases in actually being able to simulate them. However, the last decade has shown that these climate models are actually capable of generating a lot of different types of extreme events, particularly tropical cyclones is one of the first ones that pops out when you go to high resolution, and I'll show that in a second. But in generally, their intensities are generally weaker than observed. So to kind of put this into context, here's just a snapshot of Hurricane Katrina a day or so before landfall. And if you look at what a typical GCM atmospheric grid would look like from maybe 10 years ago, this is what you would see. So you would see if you're trying to resolve this dynamical process in a model that has this type of grid, it's going to be very, very difficult. And so what we've been able to do in more recent years is actually go to higher resolution. So if you If you take the same grid and now you put a 50-kilometer grid spacing, which is kind of high resolution for a climate community, you can see right away you're still going to struggle to get a lot of the important mechanisms for the genesis as well as intensification and decay of these type of storms, but you're actually, at this point, will be able to capture a lot of the dynamical fluid aspects of the events. And so maybe to harp on this a little farther, to put it in more context than just tropical cyclones. So here, it's just a plot of a typical scales we experience in the atmosphere in both spatial scale as well as time. So as you go out on the axis, you're getting larger and longer duration. And so typically, climate models have acted in this realm here, where you can run for long time periods. So you can look at climate variations. You can look at the El Nino. You can look at seasonal cycles, as well as a lot of interseasonal phenomena, such as the Medin-Julian oscillation and planetary waves. But everything else in these models is kind of under-resolved or unresolved. And so you can't get a lot of these typical features that are kind of true of weather models. So if you look at a weather model, typically you run at slightly higher resolution, so you can capture more scales. So you can capture synoptic scale, weather, cloud clusters, tropical cyclones, which pops out here. But you generally only run these models for maybe 2 weeks. And what I hope to show you by the end of the talk is that we are now entering a different range of climate modeling where we can actually start to nudge basically our scales down. So we could still run for decades, which I'll show you some simulations of, but we now push into these down into these scales where we can actually start to resolve. The first thing that pops out generally is tropical cyclones, but we can also start to get down into fronts and squall lines as well as other cloud clusters. And so just really quick, just to harp on this just a little bit more, using Hurricane Sandy as an example. This is kind of what, and you'll see this pop out as we go through. This is a standard resolution that was probably used in the 1990s for climate models. So when we were first trying to look at how the climate is changing, we kind of used this resolution. And in the early 2000s, we started to use this resolution. And so now you're starting to see more detail, and you're going to see what pops out here in a second. But you can still see that if you're trying to resolve anything smaller than those scales, it's not going to pop out. And then here's kind of resolutions that are used in the most recent version of the IPCC. So in these intercomparisons that have been used to inform policy, this is a resolution. So you can start to see that there's some structure that's starting to come out here. And then as you go to kind of state-of-the-art, the highest resolution models in the current version of the IPCC use this resolution, which is roughly 50-kilometer grid spacing. So this is kind of an example I showed you of Hurricane Katrina with high resolution. And then this is what happens, and now you can start to see the actual structure of Hurricane Sandy or of Superstorm Sandy is popping out here at 25 kilometers. And as we go to 14-kilometer resolution, which I will show you some simulations of towards the end, you can see now you're completely resolving most of the dynamics, at least, of the event that of Hurricane Sandy. And this is actually approaching. This is very similar to what a lot of the resolutions are actually used at in weather models today. And so as resolution goes down, or resolution goes up, I guess it depends how you look at it, better representation of extreme weather events. So here's an example. But there's a lot of other things you get, and I'll show some of these as we go on. You get better representation of land surface processes that pop out. You're going to get huge impacts of topography, actually, that can have huge impacts on weather pop out really quick. The interface in which you're actually doing your coupling between all the different models in the GCM improve, as well as the emission, transport, and reactions of chemical species that are often included in these models as well.
And you're running 125 resolution for the whole planet at once.
So I'll show you in a little bit. I'm only running 25 kilometers for the whole planet at once. we use other techniques to get down to here that I'll show. And so you jumped to it. And so for the rest of the talk, I'm going to show a variety of simulations here. Typically, the way I'm going to present it is using grid spacing of 100 kilometers, which is a typical state-of-the-art current generation resolution that's used. And then I'm going to show you results of what we call kind of next-generation high-resolution simulations, which have a 25-kilometer grid spacing, which is maybe roughly double what weather models are using. And these are global. So these are why these simulations are quite expensive. Typically, so for all of these, I'm going to be using CAM5, which is the Community Atmosphere Model, which is developed at NCAR as well as the Department of Energy. A lot of these simulations are atmospheric only, and so they follow this atmospheric model intercomparison project protocol. But what that means is we're basically running it very similar to the way a weather model is run. And so you don't have any interaction with the ocean besides, so the SSTs, the sea surface temperatures are prescribed based upon what they were. Or when we do future warming scenarios, we actually prescribe them based on lower runs, lower resolution runs. And so everything is generally then prescribed as observed, including the ocean temperatures, ozone, greenhouse gases, and the solar forcing. So about 4 or 5 years ago is when we first started to do these runs, when we did our first run with CAM5 using an older numerics package. And we basically ran the model at 3 resolutions. And we tried to look at how precipitation changes in a model when you do this. So the first example, let's see if I can pull this up. Nope. Looks like I lost it. Well, we'll find it at the end and I can show you. But this is just a snapshot of what basically the water vapor in the atmosphere looks like when you go to 25 kilometers. So if you just notice, the first thing that pops out is you can start to see these vortices, which are tropical cyclones. But in addition to that, you can see a lot of other detail, particularly in the tropical region where tropical convection is, as well as if you look in regions of topography. You can see the role that topography often plays in blocking circulation. And so you can see that here in the Tibetan Plateau as well as in the Andes. And so you can see you're gaining a lot of information by going to these high resolutions. One of the first things you do when you're a climate modeler and you change resolution, the first thing you generally do is you look at how your precipitation changes. So here's just an example of as you go from relatively low resolution up to high resolution, the changes you get in your annual mean precipitation. And so you can compare it to observations. So the first thing you notice is that even at the low resolution, there's some significant biases in precipitation intensity. Now it's actually playing over here. And you can see oftentimes that as you go to a higher resolution, you get more precipitation in certain areas, which means the biases that already currently exist in the models are potentially getting worse. But from one aspect, the actual global mean precipitation doesn't change too much, and that's maybe a good thing. But what we're actually interested in, what you're buying as you go to high resolution, is you're getting more extreme precipitation, which is hopefully should be more realistic. So here is just a plot of the probability of a given rain rate, essentially, in millimeters per day. And so down here, these are these really extreme rates. And so the first thing you notice is that as you go from low resolution, the green, up to high resolution, the blue, you get an increased probability of getting these extreme precipitation events. And so depending upon if you look at the globe and you use one observation, you maybe argue that you're getting too many extreme events from a global perspective. But if you look over CONUS, so if you look over the continent of the United States, where we can trust maybe a lot more of our actual gauge measurements, and there's a lot more of them, you can actually see that as we increase resolution, we actually get into the observational range of what's actually observed. So it shows you can't just use one metric to necessarily to say if you're doing better. And so one of the ways we do it is we kind of try to break it down to these areas. Another thing that you can do is you can look at extreme events, precipitation events. So one way to do that is to look at what we call the annual maximum 5-day accumulated precipitation. So this is look at any 5-day period in any year, and what is that maximum accumulated precipitation over that 5-day period. And so you can see actually as you increase resolution from the low resolution up to the high, you're actually getting some of this distribution that's actually seen in observations better. So down here you don't get any of these purples, which as you go to high resolution you're actually getting the purples. Maybe you're getting too many purples. And so you're actually getting closer to what is seen. You're starting to pick up more of a distribution. So if you focus on the United States here at the low resolution, you can kind of see there's very little, there's this east-west gradient, but there's not a lot of detail compared to observations. And as you get to that high resolution, you can start to pick up some of that detail, which is great. As well as if you look at 20-year return values. So this is a value of precipitation that you'd expect to happen once every 20 years. And so you can see the same general trend that as you're increasing resolution, you're able to capture those precipitation extremes much better compared to what we see in observations. And so these simulations have all been for basically what we call recent climate. So these are decade-long 25-kilometer simulations from 1980 to 2005, as well as the observations. So this isn't just a couple-year simulation. This is a full, basically, nearly 3 decades. And so this is some work that we initially had done with my colleague Michael Wehner at Lawrence Berkeley National Lab. But we also, as I mentioned, the first thing that kind of comes out when you do these high-res simulations is the simulation of hurricanes. So now I'm going to use these same simulations. So just I didn't probably do a good job at introducing this a second ago. So these are full atmospheric simulations at 25 kilometers and 100 kilometers. And these are completely for 80 through 2005. So these are 27-year simulations at this high resolution. And so if you run it at a typical low resolution model, this is a current IPCC current kind of class of model, so 100-kilometer grid spacing. Over the entire 26 years that we do the analysis on, these are all of the hurricanes you get. And so you can count these probably by hand. There's a couple a year, and they actually have kind of bizarre tracks. You'll notice that they kind of go more south to north in kind of full, not very curved. And so if all you do, and we make no other change to the model, but increase resolution to 25 kilometers globally, this is what that looks like. And so the colors are representing the differences in intensity. So blue, right now I'm only showing anything that's hurricane strength. And so as you go up to red, that's a Category 5 storm. So the first thing to pop out as well is actually at this resolution we can actually capture Category 4 and 5 storms. And this is important because these are the ones that are most impactful on society in general. And so right away you can see we're getting a lot more of them. Generally we're actually getting roughly 70 to 80 per year, where the globally in observations we'd expect maybe something closer to 90. So we're still probably not quite there yet. But you'll notice that the tracks are a lot more realistic. They tend to have initially this east to west movement before they start to recurve towards the pole. But if you compare these to observations over the same time period, you can see we have a long way to go yet. In terms of, there seems to be this very significant bias in the Central Pacific. So if you kind of focus here, we get all these hurricanes in a region where, in reality, you have very, very few in the last 26 years. But also there's a shift in the track length. They tend to be longer in the model, as well as a little bit more poleward. But the advantage is we are at least getting a good climatology in the sense that we are getting a decent amount of storms, so we can actually look at statistics and how these things would change using these models. So the first thing I want to show you is that if we just shed off layers of intensity, so here's all tropical storms, so these are tropical storm strengths or higher, and as we go to more storms or higher intensity, you can see we're still getting Category 4 and 5 storms in the model. And so one thing that's kind of cool to do is look at what these storms look like. So here's just the Category 5 storm in the model that formed in the North Atlantic and kind of had a very typical path of a Cape Verde storm. You can see that it has a lot of similar structure that you'd expect. And actually, towards the end of its lifetime, it goes through this extratropical transition as it gets towards the pole and interacts with the mid-latitudes. But you can see you have a very clear eye region that is precipitation-free, even at 25 kilometers. And so this tells us that these are behaving much like you'd expect. This storm would have been very unfortunate for Bermuda, as it actually hit it at a Category 5. And so you can also look at other things that are more that you have an advantage of doing as a modeler that you can't do in observations. You can actually look at the wind field in the entire 3D version of the storm. So this is just a plot through the center latitude of the storm at a given time. So you can watch this evolution of how the storm forms from an initially weak surface vortex and then develops and has this very intense vertical development of the storm. And so you can use this to compare to theory and see, if these storms are behaving as you'd expect, and that's stuff that we've done. You can also start to look at seasonal cycle. So if you just focus on the North Atlantic here, the red is the observation. So this is the average number of storms we get per month in this basin. And so typically what we see in observations is we see this peak in September. And the nice thing is when you look at the black line, the black bars, which is these high-resolution decadal simulations with CAM, with the climate model, you see that you're actually capturing a lot of that seasonal variability. So you're getting at least the maximum in the right month. You'd obviously we have a slight decrease in the number of storms through the basin as a whole. And we can look at other basins. So you can see that we do some things good in the North Indian Basin in the fact that we capture this double peak. So the North Indian Basin, due to the monsoon, actually has this peak in when it gets tropical cyclones. So it has an early summer peak as well as a November, December, January peak. And so we kind of capture some part of that. But we're definitely off, particularly in the later peak in the number of storms. And then we have two very significant biases in the Pacific Ocean. But we still are at least capturing the seasonal variability somewhat well. There's just some significant biases in the counts in those regions.
So that forms for the northern hemisphere.
Yes.
So the huge Category 5 just rips through the PGs.
Right. So we captured, I'll show those in a second. So we capture Category 5 storms in that basin. We just have not as much overall storms in the basin. And so one of the things, and this is going to be kind of a quick aside, we underwent this change in the last few years where we went from this typical finite volume numerical scheme to a new spectral element. And the reason I only mention this is this is going to increase our ability to do these type of simulations. Typically, when you run on a typical lat-long grid, you're constrained by the fact that you have this pole problem where you have one point at the pole and you have your resolution converging towards it. So a lot of development has been done in the last decade to develop new computational grids that are more uniform. And so this is, we'll be using a different model within the model. So it's a different numerics package within the same atmosphere model. But it's on a cubed sphere, which means it's quasi-uniform. But so one of the first things we did was to look at the impact of switching the numerics package on tropical cyclones. And it actually had a positive, potentially, impact. So actually, as we went to the new version of the model, we actually saw this increase in the number of tropical storms and hurricane strength storms to where the fact that the hurricane strength storms are now actually well within the observational range for 3 decades. But we're still not capturing the total number of major hurricanes. So these are Category 4 and 5 storms. So even though we are capturing some, which is shown by the red box here, we're definitely well under a third of what's actually seen in observations, which is the black box. So it shows you that we have a way to go. And so this is just a complete aside, because this is just harps back. It gave some credence to some work I did 5 years ago using a very simple idealized vortex in these same models that just took 10-day simulation. So, an unbelievable, so a couple hundred computer hours versus 5 million. And we saw this same behavior, that in this new version of the model, it always was producing stronger storms. And so this is just a plot of evolution of intensity than the older version of the model. So it shows you that we have a lot to understand about why this is. It's actually not necessarily straightforward. There's tons of literature out there that shows you if you change your convection parameterizations and a lot of other things in your physical parameterizations that should obviously have an impact on cyclones. But it also shows you that there's an impact of changing just how you do your numerical methods actually can have an impact on local storms, which I thought was an interesting result. And so now here is just kind of a summary of, so we've been doing these high-res simulations for about 5 years now. So this is kind of a summary of all the simulations that we've done. And so it's also somewhat of an advertisement, if anybody's interested. So what I've shown you thus far is the simulations with this green. So this is the plot of the storm count in the North Atlantic. So this is another way of seeing if you can capture this interannual variability that exists. Some years we have 29 storms in observations, which is the black line, and some years we have just 5 or 6. And so obviously you would hope that your model could capture some of that variability. It might be a little lower in storm count, but you would expect maybe it can get the ups and downs right. So our first version of the model, which I've showed you mostly here, had a very low correlation, which means if you just follow this green line, it did actually great until about 1992. And then afterwards, it actually is negative correlated. And so we learned some there. We went to this new version of the model that I just showed you the differences for, and that's the red line. And so we've seen an improvement. And actually, some of these runs here are actually with different aerosol models, which have gone from being just prescribed, you tell the model, you tell the atmosphere what the aerosols are, to actually being fully prognostic, where the aerosols actually, or the model predicts what the aerosols are. And we actually see that by having it being able to predict what the aerosols are as opposed to prescribing it onto them, the model actually improves its behavior. And so actually getting R values, correlations, closer into the 0.5 range, which maybe seems low if you want to do seasonal forecasting for a climate model, those are actually pretty impressive. And so here's just kind of bring this point that these models are much more complex typically than a typical weather model. So here's just, as I was mentioning, we've run with 2 different types of aerosol model, and it's known that obviously aerosols, particularly dust coming off the African continent, can actually have a huge impact on stability as well as the likelihood that storms can form in the North Atlantic in the main development region, because this is where most of them form. And so you can see that the difference is by having these fully prognostic aerosols, which are part of these complex climate models, are very, very different. So if you want to try to trace back why we have differences in interannual variability in these models, you have to really start to dive into a lot of messy, detailed stuff that can be difficult. But I'm going to leave all that behind because this has all been kind of just what has been done based on current climate. I'm going to kind of use the last little bit here to talk about future changes. So this is going to be focused only on tropical cyclones to this point, because a lot of this work is preliminary. But what we've done, in addition to running these modern runs that I've already shown you, these kind of recent climate runs, we've also done simulations with these these pathways into the future. So these are 2 different scenarios of greenhouse gas warming, as well as we've also done some, and I'll show these initially, some climatology runs. So it's actually unclear how you project, especially a model that is not coupled. So since we don't have an ocean, we're just prescribing it for computational constraints. It's hard to actually know how to run these type of simulations. So there's 2 ways we do it. One is we just take a climatology, which means we run the same year over and over and over again. So we run basically 1990 over and over again, and then we put some uniform simplified changes. So we increase the SST or we increase the ocean temperatures by 2 degrees everywhere to try to mimic what warming might look like. And so this is what we did initially about 3-4 years ago. But now we can do these more intensive actual forcings that using SSTs from lower resolution coupled runs and then using them as the boundary conditions for a high resolution run. And so I'll talk a little bit what the difference is between these. But the first thing that you see is that here is an example of a climatology run. So this is when you just run the same year over and over again for 20 years or so. And this is what the cyclones look like. So if you think back to the one I showed you of where we actually used observations to force the run, it's relatively similar in terms of distribution, and that's kind of to be expected. But we can do these things where we just increase the ocean temperatures everywhere by 2 degrees. And so this would be maybe a very idealized format of what a warming climate would do to the ocean. And you can see there isn't necessarily noticeable changes. If you dig in here, you actually can see that there are more of the hot colors, which means the storms are maybe getting more intense. And then we can also do things where we double the amount of carbon dioxide. But since it's not a coupled model, that doesn't necessarily have too much of an impact. The only thing it actually impacts is atmospheric stability. And I'll show you a little bit what that means in a second. But in general, what you can see when you do a uniform idealized forcing of climate change, you don't see too many differences in distributions. And so what the differences you do see are a little bit more subtle than that. So here is a plot. And what let's just focus on for here is just this, the blue line, which we'll call the current climate run, and the purple one, which we'll call the climate run with 2 degrees warming everywhere. And so what you see, first thing you notice is that in all hurricanes or tropical storm strength storms, you see a decrease in the number. But if you look at really intense storms, so category 4 and 5 storms, you actually see a very significant increase in the number of more intense storms. So we're getting less storms, but they're becoming more intense. And this also holds true if you actually include the doubling of carbon dioxide in the atmosphere. And another interesting thing also occurs if you look at the average storm duration. All storms are actually getting longer in duration, including the storms when they're at their highest intensity. The nice thing about a climatology of storms as opposed to year, where you have this kind of variability, is you can kind of just look at maybe if there's shifts in track. So this is now just kind of a density of where storms form as where storms go. And so this is latitude. I guess I didn't have a good bar here. So this is from about -40 to 40 north. And so the really thing to notice is that as you look at these simulations, as you go from the blue to the purple again, you'll see this in both hemispheres. Not only is there a shift by a couple degrees in the regions of genesis where you actually get storms forming, and this is obviously due to the fact that you have warmer temperatures farther north in these regions, and so there's potential due to the actual spinning of the Earth, for these storms to form. But also, there's an even larger shift in where the storms actually go. So this means that the tracks are tracking farther north when they're and peaking farther north than you actually see in the current climate. But these are idealized, and we know that the impact of the SST pattern, the ocean temperatures, the pattern of the ocean temperatures, actually has a huge impact for tracks of cyclones. So we don't actually necessarily use these as much as we'd like to. They were kind of just our first runs to see how these general characteristics of cyclones change in a warming climate. And so we've done these runs now that are much more realistic. So we're actually running a low resolution kind of IPCC version of the model. And what we're doing is we're just taking then, and that would be a fully coupled model. And so then we take out the ocean temperatures from that model, and then we use it to force our high resolution atmospheric model. And so
what resolution does the low resolution?
It's a 1 degree, yeah.
So how about the ocean?
So the ocean would be a quarter. It would be the CMIP version, so it would be a little bit higher resolution. So this is actually the CESM large ensemble. And so again, a lot of the signals that we saw on the idealized forcings come out. So we see this significant decrease in the number of storms on the globe, as well as a decrease in the number of hurricanes, which is interesting. But we see this doubling of the number of storms that are category 4 and 5. And so that's great. We have this general concept, but now we want to actually know, are they changing? Where they're going, is that changing? And so what we see initially, and so this is now a track density. So this is basically the number of storms that is in this point every year. Or generally, we actually do in a 4 by 4 degree box. But what you see is that the decrease in intensity as you go from present day to the warming scenario, or a scenario that has less warming, is actually pretty robust across the entire globe. So every basin is actually seeing a decrease. It isn't that one ocean basin is seeing a larger decrease than another. And so what we've done is we've started to focus. So this is just zoomed in on that plot. And we're going to focus on the North Atlantic here, which is important to us. And so here on the top now is this track density of all storms that were simulated in the recent climate using 3 different ensemble members. So we are just now entering a frontier where we can actually run ensembles of these, which is important. And so we see, okay, here's the current climate, and here's 3 ensemble members into the future. So these are 2070 to 2099. And so you can see there is a pretty robust decrease across the board in all ensembles. So this gives us actually more credence, and we can believe that there is, at least the model is simulating a significant decrease in the number of storms in the North Atlantic in a warmer climate. So that obviously has repercussions for society, potentially. But what we have to be careful about is that the ocean temperature that we force these runs with, were just one realization of a low resolution run. And so what we're starting to realize that is if you run a low resolution climate model 30 times, you will get drastically different results in what sea surface temperatures would look like across the globe. And so what we've showed here is 2 different forcings of the future ocean temperatures using or from a lower resolution model that produced a different type of basically ocean temperature in the North Atlantic. And what you can see is that depending upon what your sea surface pattern is, your pattern in the future of where storms are is very different. But the thing to keep in mind is that the actual decrease in the storms is still present. It's just where the storms are. So we're maybe getting to the point where we can actually use these models to actually argue whether storms are increasing or decreasing in a basin. But we're still quite a ways away from being able to say, these storms are more likely to hit the mid-Atlantic than they are the Gulf of Mexico, which is unfortunate, but at least we're making progress. And we can do the same thing for the West Pacific. So this is an area where we typically have a lot of really intense storms, as was mentioned earlier. So these are for Category 4 and 5 storms. And so as we go to the future, we see this very robust increase in the number of intense storms in the West Pacific. But depending upon your pattern of ocean temperatures, where those storms go can change pretty significantly. So we still have a way to go. We can also look at the precipitation within these storms and see if they follow some theoretical expected changes that should occur. So here is basically just a plot of the frequency, and just focus on the black line and the red line. So this is the present run, and this is the kind of RCP 8.5. So this is this intense warming scenario. And so what you see if you look down at the extreme precipitation within the tropical cyclones, there's this very significant increase in the intensity rates. But if you assume if you pick at one rate, I mean, the chances of getting something that's maybe 80 millimeters per day in a tropical cyclone is 200 times more likely, or 100 times more likely than it was in the present climate. If we scale this analysis by the expected change in the saturation of the atmosphere due to the warming, so if we scale it by basically a Clausius-Clapeyron, what we expect to change by just increasing warming, you'll see that those lines come together. So a lot of this is just due to the fact that the temperature of the atmosphere is getting warmer. But it doesn't explain all of it. So it tells us that in extreme events, changes in precipitation can actually be super Clausius-Clapeyron. So they can potentially be larger than you'd expect just by increasing the temperature. And so I want to take the last few minutes. So I've mostly showed you tropical stuff, but there's a lot of other colleagues have been working on aspects of this for different extremes. And so the first one I want to show you is is northeast snowfall. And so This is now where we're getting into another exciting atmosphere of regional climate modeling. Instead of using regional climate models enforced by large-scale or larger-scale climate models, what we can actually do is run the climate models in these variable resolution setups. So you can basically have 1 degree model. You can have a standard current climate class of a model in behind in the background, and then in the area you're interested in, you can zoom in basically. And there's a lot of advantages to this technique because it's dynamically consistent across the model. And so you can use this to focus on areas that you're interested in or particular weather phenomena that you're interested in. And so this is some work that Colin Zarzicki at NCAR has done using these type of models. So if you use a typical current version of the climate model and you use this variable resolution with high resolution in it, and you look at snowfall in the Northeast, right away it pops out that as you go to high resolution, you're getting a better distribution of snowfall. These scales are off, so just look qualitatively. And so you're capturing some of these areas where you have lake effect snow a little bit better than you were before. You're definitely capturing the topography impacts of snow. So this tells you that at the low resolution, there's a lot of things you're missing because your mountains are too smooth. And so I just wanted to chat real quick about the advantages of these variable resolutions. So in that setup, for example, if you were to run the whole model at the 25 or 28 kilometers to get that same analysis just for the Northeast, for example, it would cost you 10 times it does to just run a variable resolution version over an area of interest. And so this means you can run 10 ensembles, which really improves our ability to do science. And the same thing can be true, and I'm going to show you some now results as we go to 14 kilometers, which is kind of now pushing this range of what weather scales are. And you can get some really significant speed-ups by using these configurations. So some work that colleague Paul Ulrich and his student at UC Davis have done, Alan Rhodes, is they've looked at these atmospheric rivers. So atmospheric rivers are important to precipitation, particularly in the Pacific Northwest and California. It can produce generally up to 50% of their annual precipitation comes from these 2 or 3 events a year of these atmospheric rivers, which are these very fine filament structures that transport huge amount of moisture from the tropical regions right to the coastline where it impacts the topography and dumps huge amounts of rain. They're interested in this because they want to look at the applied aspects of western snowpack to help project potential changes in this snowpack and for planning of when to let water out of dams and not in the area. And so this just shows you the topography. If you go from a low resolution version of the model to this high resolution 14 kilometers, you can see you're now resolving all of these mountain ranges a lot better, and which if you just watch this video, you'll see at times when the precipitation is coming through, you'll see the mountain ranges pick out. So by capturing this ability to get the topography right, you're actually going to get the regional climate better. And another example of this that we're doing is instead of just doing climate simulations, so these are all generally multiple years, we're actually now starting to test these models kind of in more forecast-like simulations. So the idea is now that we're approaching weather resolution, can we actually treat these models to some extent as weather models to use them to validate them, so when we do regional climate assessments, we actually know that they're actually doing a really good job of predicting weather potentially as well. So this is some other work that Colin Zarzicki has done using a low-resolution version of the model over here, and then using this variable resolution version that goes all the way down to 13 kilometers, or a globally 13-kilometer simulation. And this is the spin-up of Hurricane Sandy. And so you can see in the higher resolution versions of the model, using this kind of mesh down here, you're capturing a lot more of the details of what goes on. And so this allows us to maybe validate these models in not just the climate sense, which I showed you a couple slides ago where we looked at the climatology of tropical cyclones, but how well does it do at actually modeling actual tropical cyclones. And so here's just an example of the forecasted track using this variable resolution setup. Is the ensemble mean for CAM is the blue line. And you can ignore the green line. And then the GFS, so the operational forecast model, is in red. And so these are at different forecast lead times. So the thing to actually pick out is that CAM, our climate model, at the same resolution as GFS, actually started to pick out this recurvature, this recurving of Hurricane or Superstorm Sandy earlier than the actual forecast model did. So it shows you that there is some skill in using these models. We're not arguing that you should actually use these for forecasting weather, but the idea is that you can use them to validate, you can use the actual weather events to validate their ability to do it so that when you do these regional climate impacts, you can trust them a little bit better. So I'll finish real quick. So just some final thoughts. These decadal simulations, at least of tropical cyclones, seem to compare reasonably well to what has been observed, but there's still significant biases that we're working on. We tend to believe that as you increase a lot of the biases, as I showed you initially, even in the low-res versions of the model, you'll actually start to correct a lot of these biases in the extremes as well. As the climate warms, we see a decrease in the number of tropical cyclones, but the most intense storms are becoming more intense and possibly more frequent. And so these decadal ensemble simulations, we're just now starting to do these things, but they definitely are shedding light on regional changes in tropical cyclones, but there's still a lot of uncertainty in pattern of future distribution of storms, which is probably more important than just knowing what the counts are changing. And that there's a lot of other examples now of other researchers that are applying these high-resolution approaches to other extreme events for regional impacts. And so I'm just going to, yeah, I'll finish with that. That works. Thanks.
So when you show the comparison between your observation and the simulations of different resolutions, you show that when the resolution getting higher, the extreme precipitation region also, the precipitation also getting heavier. But
right.
compared with the observation, it is way heavier than what we observed. Is there any specific explanation for that?
So one of the explanations is that, so you allowed me to use one of my backup slides. So part of the thing that we're seeing is that oftentimes in low resolution, it's raining too often, but not hard enough. And so we go often the opposite route when we go to the high res. So we're getting too high of intensities, but the frequency is improved. And so these why this is really linked back to the basics of what the model is built upon. And so a lot of the assumptions that are made in these parameterizations, and this is kind of the big caveat to a lot of this work, is these models were developed to be run at 200-kilometer grid spacing, and we're now pushing them into a range where they were never built to do. And so a lot of the parameterizations aren't probably necessarily behaving properly or maybe overactive. Actually, in this argument, so my understanding of what's happening for your question specifically, is that the actual parameterizations aren't doing enough. And so what's happening is all resolved scale condensation, which is too intense at such a coarse, still relatively coarse grid spacing.
I have a follow-up.
Yeah.
There's a joke saying if we cannot explain it, we blame it on the aerosols. So I just wonder, did you have any experiment to compare the effect of aerosol?
On precipitation itself?
Yes.
Or? No. No, we haven't done that. We have started to do some runs where we actually change parts of aerosols, but we've never actually done any sensitivity. At least I haven't. I'm sure when they developed the model, there was stuff that was done, but yeah, I haven't.
Thank you.
Yep.
Is there an explanation that mere mortals can understand as why the number of extreme events goes down as the climate warms?
So, no. So, well, it depends on who you talk to, I suppose. There's a lot of potential theory. I mean, so one of the ways you can think about, the way I think about it is, particularly for tropical cyclones, so there is an absence of actual theory on this. So without actually a theory of how hurricanes change in a warming climate, actually climate models are kind of our only tool right now, one of our only tools. There's a lot of other techniques using statistical or dynamical downscaling. But the idea is partially if you are getting more intense storms, if they're getting more intense than they should based upon the environment, which shows you that this, I showed you with the precipitation, they're actually producing more strength than maybe they should just based on the temperature change alone, that they're actually taking more energy out of the system that would have been there for other storms to develop later on. And so because they're becoming so intense to begin with, that's actually decreasing the number of potentially weak storms that can form. The other idea is that, and one thing that we haven't really been able to do yet, is it's quite possible that a lot of the triggers for these tropical cyclones are under resolved or are changing. So if you look at the North Atlantic, 80% of all intense storms in the North Atlantic generally come from African easterly waves. So these are these large-scale phenomena that come off of Africa due to the dynamics of what's going on in the region. And so it's quite possible that if there's any shift in those wave patterns ever so slightly, that can have huge ramifications for the triggers of these storms in those basins. And so it's possible that not only the storms are changing, but the precursors to them can be changing. And so perhaps the efficiency of triggering a storm is actually decreasing.
I would like to go back to Eric's first slide. And it's because I'm interested in the precipitation.
Mm-hmm.
And did you try to look at whether it could be just the convection schemes are not just suited for this?
Yeah. So one thing I haven't even mentioned is that the convection. So all this work is almost out of date to some extent because we've already now the community is the model has already changed and will be changing for the going future. And so one of the things we did is there's been a wholesale change to the convection scheme. To a scheme that's supposed to be more scale relevant, meaning it's multi-scale. It should actually be able to handle these shifts in resolution better than the current version. So it is. I mean, I argue a lot of what's happening already is that these current versions are not suitable for what we're actually using them for. They're definitely not made for extremes. They were made to look at general climate.
The high resolution, the tropical cyclone in Western Pacific decreased, but the Central Pacific increased. Why is that?
Say that again.
The tropical cyclone, you showed the track, the high resolution.
Yeah. So here.
Yeah. So the previous.
So this is observation. So here.
Yeah. This is the observation.
Yeah. So.
In the Central Pacific, there's a huge increase.
Yes.
Why is that?
So one of the ideas that we've been trying to look at is that you can see generally in the Eastern Pacific the tracks are very constrained to a certain area. And if you go and look at, I'll go back, sorry. What's happening in the model is they're not nearly as constrained. And so what's actually happening is the intertropical convergence zone in this region is actually extremely overactive. And that's actually, you see that in those precipitation plots. And so it's a lot more efficient at spinning off these small-scale vortices that are developing in tropical cyclones. And so the idea is that it's spinning them off far enough down here that they can traverse. Without a fully coupled ocean model in this area, these storms are not necessarily mixing up the ocean at all, so they can actually form in a region where they maybe would have decayed pretty quickly. Yeah, so there's definitely the intensities. If you were to run with a coupled model, these would all be generally slightly weaker, but not by much. So some other people have done that. But there's definitely a feedback from mixing of the upper layers of the ocean that can cool the SST some, which cools the storms. But the problem with running, there's only been one run that's ever been run coupled at this resolution. So when you add in the ocean, it over doubles the cost of the run, and it already is costing a couple million computer hours. And those models, we don't understand a lot of the biases so poorly, I guess, that the biases in the ocean model and such things like ocean temperatures get so bad at this resolution that you actually don't get storms in a lot of basins.
There's a huge void around South America.
Yeah.
Above the ocean.
Yeah. So this is something that's seen in observations as well as the model. Actually, one interesting thing is if you go to a lot of other modeling groups, Most climate models actually simulate a few more storms than we've actually seen in reality there. So a lot of it is, I mean, a lot of the requirements that you need for storms in these regions don't exist. But it is still actually an active area. I mean, we kind of have these ideas of why we don't get these. A lot of the triggers there you need for storms are not there. But it's actually it's an interesting area. So it's interesting because if you could try to use the model to understand better why it doesn't form there, then you could probably actually learn something about cyclogenesis that you don't know.
Okay. Let me ask you a final question here, and then we'll take for lunch. So you're showing that sort of the scale when you sort of prescribe as a T goes up to maybe 1.5. But I've seen some presentation by JPL when they say show the similar scale that goes up to 0.8 or something like that. So does anyone understand why they are doing so much better than it?
GFDL.
Yeah. GFDL.
So I guess.
Yeah, the same resolution.
So I guess the political way I'll say this is that for all of our simulations, we have done no modification to the model. So we take the low-res version of the model, and we run the model with all those same tuning parameters. All we do is increase the resolution, we decrease the time step, and we run it that way. We do no tuning. We don't look at tropical cyclones until the model is done. And so we've never had necessarily an interest to this point of making sure the model is good at tropical cyclones. We've only tried to see what we gain by going to high resolution, which is different approaches for different modeling groups.
So yeah, let's thank the speaker again.
Go die.